Functional programming, or FP, has become an increasingly popular programming paradigm. However, the transition from traditional programming to FP can be challenging. This talk aims to bridge the gap by providing a comprehensive introduction to FP, and demonstrating how it can empower your development. Our speaker is passionate about exploring concepts and ways to code to prevent bugs from ever occurring. Show some love to Senior Software Engineer for J-Driven, Mr. Tees van de Ven.
Hello everyone. Actually nice to see that AI pronouncing my name correctly. You don't see that often. Hello Softron, very nice to be here. And welcome to my talk about functional programming, or is it really about functional programming? We'll see about that. First, a bit about myself. So yeah, I'm Ties van de Ven. It's morning here because I live in the Netherlands, as you may be able to tell by my accent. My background is in Java, Kotlin, and Scala, and I'm a bit of a functional programming advocate. That's not completely true. I'm more passionate about software engineering fundamentals in general. So more the why instead of the how. And I found out if you basically go into the why long enough, you kind of end up with functional programming, but a bit more about that later. Another passion of mine is sharing knowledge. That's why I'm doing stuff like this, speak at conferences, speak at Java user groups. I also do a lot of individual coaching and such, and giving trainings. And I would invite all of you to do that as well. Sharing knowledge is basically the only thing that expands the more you share it. So if you ever want to be on a stage like this, but don't feel really comfortable or something, feel free to add me on LinkedIn and maybe we can help. I'm also active on Coding Coach. It's a website where you can sign up as a mentee or a mentor if you look, and basically you help each other for free. So if you want mentorship, go to Coding Coach. If you want to look for a mentor or even me, go to Coding Coach as well. So enough about that. What are we going to talk about today? Just finished the introduction. We're going to talk a little bit about what functional programming adds to it. To the programming, and our four main topics are composition, state management, error management, and side effect management. Well, out of these four topics, I would say composition is the only real functional programming thing. The other three are mostly mentioned in the terms of functional programming, but I would say these are more fundamental problems. No matter the language, no matter the paradigm, you always have to deal with these three things. That's why I think it's really weird that I mostly mentioned into a functional programming context. Because I actually had a use case where the team actually said, no, we're not going to do immutable objects because that's a functional programming thing, and we're doing object-oriented programming here. And I think this is a bit of a shame. As Brian Getz also says in one of his talks, don't be a functional programmer, don't be an object-oriented programmer, be a better programmer. Learn from both paradigms and apply the patterns where needed. And often that's a combination of the two. So why are these things mostly mentioned in terms of functional programming? So I did some thinking about that, and this is my current theory about that. It's a bit the same as physicists versus mathematicians, where in mathematics, mathematicians get some ground rules, the axioms of mathematics, and their job is basically to figure out what universe is possible given those rules. On the other hand, you have physicists, where they basically get the universe and trying to figure out what the rules are. And I see this concept quite a bit in software engineering as well, where the people who mostly do functional programming are people with an academic background. I don't have an academic background myself. I rolled into it, but a lot of functional programmers have an academic background. they basically, when they studied at university, they learned the ground rules of software engineering, the fundamentals, and slowly started to learn to be able to be productive. Most software engineers that I met, however, including myself, basically went to school. I learned to be productive, and I slowly started to learn the underlying concepts of why stuff was actually working. And because most of the fundamentals and such are taught to the academics, and they do a lot of functional programming, I kind of think that that's the reason why these things are often associated with functional programming, but they are by far not limited to functional programming. So why would you consider the functional programming paradigm? Well, it has three very good properties. One of them is reusability. If you think object-oriented programming is reusable, functional programming takes that to the extreme. That's also why you get these incredibly unreadable functions. That's all because they want to maximize on reusability. Another big part of functional programming, and it's quite infamous for that, it's terminology. So in functional programming, people like to talk about monads, monoids, functors, semi-group, etc. the bunch. I'm going to promise in this talk, this is basically the only time I'm going to mention these terms. We're not going to talk about all those terms. We're mostly going to talk about the problems functional programming tries to solve. But there is some value in learning this terminology because it's how your brain works. The moment your brain has a certain word for a concept, it starts to actually process data differently. So it can basically take a shortcut. Instead of having to have the whole concept in your head, you can just think in terms of that single word. This is also why language is so important, because it allows you to think in a certain way. So learning functional programming terminology can actually help you become a better programmer because your brain starts thinking in different patterns. And it's also good for communication. To be fair, a lot of functional programming terminology is on the internet is quite difficult to get through. So if you have any question on that, feel free to ask me and I'll try to help. And the third thing functional programming is really good at is complexity management. So if you have a very complex application, functional programming, most of the things it tries to do is try to manage this complexity. But there's a big downside here because not all applications are very complex. A lot of applications are actually quite simple, like quite trivial applications. And the irony is, if you apply complexity reducing measures to an application that's already incredibly simple, ironically, you make it more complex. And this is one of the reasons why functional programming is hard to explain, because you don't want people to give a whole monolith application to people and basically say how functional programming improves that. You want to teach by examples that are easy to follow. But those tend to be so simple that some functional programming things make them more complicated. So this is basically makes explaining functional programming quite difficult. And also there are some functional programmers who are quite dogmatic in the sense that, no, you have to apply these patterns everywhere, no matter the application. And that's also why functional programming can get a bad name, because they try to reduce complexity in applications that are incredibly simple. So you have tons of applications from trivial to extremely complex. And with simple applications, you can get away with a lot of things. You don't actually have to do a lot of things. It will probably just work. But the more complex your application gets, the more of these complexity reducing measures you will need. Otherwise, the complexity will grow out of control. So the truth is your application would be somewhere on this line. And that just means that all the things we're going to talk about today, you don't have to apply them in every project, but the more complex your project gets, the more you kind of need to apply these patterns. And that brings us to our first topic today, composition. So in composition, mostly function composition, function signatures are key. And a function signature is composed of the input and output of a function. So if you take the top function here, it has a person as input and a name as out and a string as output. So the function signature is person to string. The length function has a string as input and an int as output, so its function signature is string to int. And composition just means that because person outputs a string, and of the first function outputs a string and the second function takes a string, we can combine those and create a new function that straight goes from person to integer. And this is basically the idea behind function composition. A good way to visualize that is like the original domino game, where every tile has an input number and an output number. So you can see every tile is a function which requires a certain input and a certain output. And while individually they can be incredibly simple and don't do a lot, however, if you combine them, you can create quite a complex program. So how does this work in code? Well, if we just have a problem here, given a list of persons, sum the total age of everyone with the name starting with A. So I'll give you a second to think about how you would solve that in Java while I drink on my bit out of my ridiculously large mug. So a lot of people might come to this solution using a for loop. This is, for the record, a perfectly fine solution for this problem. So if you come to this, no shame to you whatsoever. So we have a total length variable, we list over the persons and filter out everyone who starts with an A and increase the total length. The nice thing about when you came to this solution is to take a step back and figure out what your brain actually did here. Because if you look at the problem again, given the list of persons, sum the total age of everyone with the name starting with A, this problem is actually composed out of 3 sub-problems. First, we select everybody who's with the name starting with A, then we get all the ages, and then we sum all the ages. So if you came to this solution, what your brain automatically recognizes the 3 problems and combine them into one solution. So good job on your brain, but it actually helps if you start doing this explicitly, because then you train your brain into thinking, dividing problems up into sub-problems. And this is the reason why I love the streaming API, because the streaming API really resembles breaking up problems into sub-problems. Because here we see, if we stream over the list, we indeed filter everybody who starts with an A, we map people to the ages, and then we sum up the ages. Basically exactly what the problem says we should do, or the 3 different problems. So this is a very good way to basically teach yourself how to do this. And if you're not convinced about composable problem solving being a good idea, I assume we have a lot of programmers who here uses Linux or likes Linux. I see a few thumbs up. One of the main things, like I'm mostly a Windows guy, if I'm honest, but I can't work without Linux subsystem anymore. I must admit that. So in Linux, this is the feature I like the most. It's the pipeline symbol. It basically takes the output as an input to another output of one program as an input to another program. This is just function composition. So if you were ever confused by functional programming and such, if you use Linux and you like this function, you're already doing function composition, which is functional programming. And this is the reason why the Bash shell is so powerful. It's just function composition. And this composition is also very good if you want to get better at problem solving, because most of programming is actually just problem solving. I remember in the beginning, when I heard a problem, I would immediately start coding. And these days I notice more and more, first get out my pen and paper and actually work out what the problem is before solving it. And this is because once you solve the problem on paper, implementing it is usually a lot more trivial. So programming is mostly problem solving. And as we just learned, problems can be divided into smaller problems. So if you take a look at modern microservices and take a very abstract look back, we can basically define them as this. We have some JSON, we put it in a program, and it outputs some JSON back. There's just an incredibly abstract look of most software we're building today. So any problem can be mapped onto this problem. What we can then do is see if we can divide our program into two separate problems. So for example, our program first needs to parse some JSON to create some parse input that goes into a logic, and that spits out some JSON. And we can keep dividing up again. Like our logic first probably needs to enrich some data. So we get some enriched input that we put into some logic, which put into data. And we can keep on splitting the problem up, and up. And until in the very end, we end up with lots of very, very small functions that chain together form the solution for your entire problem. This is basically the method I use to, if I face a complex problem, on how to solve it, how to deal with that. Because it's an incredibly powerful way. Because the nice thing about this is we're not even discussing which language we're using here, or which programming language, or even which framework, or is this one service, or are there multiple microservices? Because no matter the how we pick, these are all the steps that are needed to solve our problem. So we're just focusing on the problem-solving aspect of it. As you can also see, I reason here in state changes. So I go from an input to a parsed input. I go from parsed input to an enriched input. That's my brain thinking in state transitions. And this is a very powerful way to reason about software engineering, which we'll see a bit of later on in this talk. So if you're ever in trouble, have a difficult problem to solve, give this method a go. Just write down the program in its very most simple state and just keep on breaking down the problem until you come up with a solution. So the key takeaways of function composition: most problems are compositions of subproblems, and the streaming API is a very good way to both symbolize this and also practice your brain to do these kind of things. And that brings us to our second main subject, state management, the most difficult problem in software engineering, in my opinion. So what is state? Basically, all the values within your application. Every bit of variable you hold on that contains a bit of state. And state is responsible for a lot of complexity. And to give an example of that, what if I would have a red car and I want to turn it into a blue car? So an object-oriented programmer probably would choose an approach like this, because object-oriented programming kind of tries to model the real world. So in the real world, if I would have a red car, I would just probably bring it to a garage and get it paint blue. So in object-oriented programming, you basically call a setter, and now my red car is blue. A functional programmer would do it slightly different. What a functional programmer would do is would take a very good look at the car, build an exact replica of that car right next to it until it needs a paint job, then it paints it blue, and then it destroys the red car. And now the functional programmer has a blue car. To be fair, in real life, this might not be a very great financial decision to do. But in programming, this actually has an advantage. Because what if I ask my object-oriented car, what color are you? What is the answer that I'm going to get back? Is it red or is it blue? The question is, I don't know. It depends on when I ask the question. But if I ask any of my two functional programming cars, what color are you? I will always get back the same answer. And this is why mutable state is inherently more complex than immutable state. Because mutable state always has the added complexity of time. Suddenly, the state of your application depends on when you ask the question. So, and this mutable state gives us a lot of problems. For example, any times you have race conditions or any concurrency problems, these are all problems that come out of state. And this is the point where a lot of functional programmers go into how immutable state is better for concurrent programming and such. I'm not going to do that because most people don't actually build concurrent applications. And I'm mostly going to focus on the other effects that immutable state can have on your code, because it can really help reduce cognitive load. So to give an example of cognitive load that mutable state causes, if my input is a mutable car, I print out the mutable car first, then I call a method paint on it, and then I print out my mutable car again. The question is then, do these two print statements print out the same thing? The answer is, I don't know. It really depends on what the method paint actually does. Does it paint our car, basically change the color of our car, or maybe does it make a painting of our car and actually doesn't alter the car? The only way for me to actually know what's going to happen here in this bit of code is if I go into the paint methods and hope there's not a whole function chain I have to go through just to figure out what this bit of code does. And this is the danger of mutable state. So what if we instead make an immutable car? Now here we can use Java 17's immutable classes called records for, where if you make something a record, set of getters, equals, and hash code will be generated, but no setters. So once you create this immutable car, you can no longer alter it. If instead of the mutable car, our function now takes an immutable car, and then ask yourself the question, do these two print statements print out the same thing? The answer is yes, they print out the same thing, because car is immutable. So no matter what this function paint does, it cannot mutate the car. So without having to go into the whole paint method, I can instantly tell something about this bit of code, just because we're no longer using mutable state. And this is the power of immutable state. You can instantly tell things about a bit of code without actually having to look at all the code. So that's why it really helps in reducing cognitive load. But we still need to change values of objects now and then. So how do we do that with immutable objects? Well, the only option we have is return a new object which contains a different state. So if we want to have a method paint blue, we will return a new instance of immutable car with exactly the same fields as the previous, as the car that we pass as an argument, except the color is now blue. But the nice thing about this is, once we add this to our function, we can now see that paint blue, it returns a new car. So if I see this bit of code and then ask myself the question, do these two print statements print out something different, or do they print out the same thing? I could tell they're probably going to print out something different, because there's a clear state change here in the code. I can instantly see where the state change in my code lives. So this doesn't solve all problems regarding the state, but at least state changes now become explicit. You instantly know when you see a bit of code, what's the behavior going to be like. And this is the power of immutability. Of course, like everything in software engineering, everything is a trade-off. Anyone who tries to say that one thing is perfect for everything, that person is either lying to you, trying to sell you something, or both. So everything is a trade-off, everything comes at a cost. Same with immutable objects. For example, performance is quite an issue with immutability. To be fair, the performance issue comes that if you want to do a lot of state changes, you have to create a lot of objects. And that can cause up a lot of memory, or can use up a lot of memory. However, in my experience, most applications I ever worked on, I think you would need a pretty good profiler or measurement system to actually measure the difference. Because most of the time, you basically only have lists of like maximum 100 items. if you map all those and using immutable objects and create a new object for all of those, you don't notice that. So while if you, for example, I don't know if anyone here knows Advent of Code, like the yearly programming competition. I try to use immutability there, but then you have to do operations on things like a list containing 2 billion elements. Yeah, that's the point where immutability really doesn't work. So my advice usually is start with immutability, and only when certain bits become a problem, then go into mutable state. So there's nothing wrong with mutable state. It's just that it shouldn't be the default. And if we're going to use mutable state, there's another trick we can use. For example, if we have a function that has to append a 0 to a string like 1,000,000 times, yeah, that's something you don't want to do with immutable state. But the trick we can use here is to make sure that our function has an immutable input and an immutable output. This way, the rest of our application still sees immutable object in and immutable object out. So for what the rest of the application is concerned, the state is immutable. So mutable state is fine. It's just that you should try to keep it function scoped. So as long as it's function scoped, it's usually thread safe and easy to use. And basically, no other part of the code will notice that you're using mutable state here. And this is also a thing where a lot of functional programmers become very dogmatic, because they're going to say, oh, you're declaring a mutable variable here. That's not good. That's mutable state. That's evil. That's just not true, because the rest of the application won't notice this if you solve this using a for loop or if you solve this using recursion. So as far as I'm concerned, mutable state is fine as long as you try to keep it function scoped, so at least it doesn't leak out to the rest of the application. And another big subject when talking about states is a phrase functional programmers use a lot, is making illegal states unrepresentable. So basically, if something isn't allowed to happen, then the code shouldn't allow it to happen, to represent that failure state. This is a whole separate topic. I could talk quite long about this, so I'm going to pick out one thing that's a bit of a pet peeve of mine, and that's nullable fields. Because I programmed Java long enough that I hate null pointers, and I don't think I'm alone in here. Everybody hates null pointers. And the trick is to prevent null pointers. I found out what works best for me is just try not to use null. And if you just don't use null, then you don't have null pointers. But some nullable fields are different than other nullable fields. So some fields are really truly optional fields. For example, if we have a person, the middle name is, yeah, not everybody has a middle name. I happen to have one, but a lot of people don't. So this will be an example of a truly optional field. However, not all fields that are nullable are actually optional. If we would take a look at a contract, for example, which has a contract text and a signature. So if the signature is null, the contract isn't signed. And once the signature is non-null, it's now a signed contract. So is this really an optional field? No, not really. It actually only, it will probably start null, but it should at some point become non-null. But the problem is, because it's a nullable field, we now have to add these kind of things all over in our application. And before we want to start a project, we actually do need to check if that field is indeed null or not. So we need to apply a lot of defensive programming here. Well, again, if you think about it, is it an optional field or is it a state change? And if it's a state change, we can also model this in our type system. So what if we make a separate class record, which only contains a text, and a separate class signed contract, which has a text and a signature that are both non-null? And at some point, if it's an unsigned contract, you use a contract, and otherwise you use a signed contract. Now, this doesn't solve all problems, because sometimes you need to have a list that would contain both and such, but For all those things, there are solutions. But if we use this as a concept, basically model our state transitions as types, just as I mentioned all the way when I was talking about function compositions, thinking in state changes, suddenly we need a lot less nullable fields. Not only that, in our architecture, our start project function can now ask for a signed contract. So instantly it shows intent. I'm only allowed to start when I have a signed contract. And because I now have a signed contract, I don't need to do any null checks anymore. So if you start to model state transitions as separate classes, what you see happening in your code is that all the checking logic starts moving to object creation of the signed contract. And anything after that in your application won't need any checks anymore. So this also cleans up a lot of your code. So this isn't an ideal situation for all problems, but it's something that should be a tool in your toolbox and consider within your code. So the key takeaways here: state is difficult. Mutable state isn't inherently bad, but it always adds the complexity of time. So be careful with this. And if possible, try to keep mutable state function scoped. And the Java type system, we can use it to remove null values and model state transitions instead. And that brings us to error handling. So things will fail. Connections will drop, you will get internal overflows and such. Errors are just part of programming. And if you take a step back, most errors can be divided into two separate categories. You have recoverable errors and unrecoverable errors. So a recoverable error is an error that can be recovered in any way. For example, by using a default value. We couldn't do this, but we can use this value instead. Sometimes you have the option of having an alternative code path, like, oh, our database isn't available, but we still have this cache we can get values from. So we'll do that instead to recover. But even returning a different status code is a way of recovering. For example, if input validation, if the input isn't correct, you recover by giving back a 400 status code saying the input is not correct. So any different status code than 200 can also be a way of recovering. And unrecoverable errors are basically anything that returns a status code 500, the technical errors. So that's basically the rough way to decide if is an error recoverable or not. Would this return a 500 or any other status code? And in Java, there are three main strategies people deal to handle errors. The first one being hope. Let's just hope they don't happen. And this is a very, very popular strategy. Not necessarily the best strategy, but it's very popular. Also, I see a lot of runtime exceptions and returning null. So let's take a look at those. So I have a function here called divide, which takes two doubles and returns a double. So its function signature is given two doubles, I return a double. But because we cannot divide by 0, because then the universe would implode, we have to do a check. And if the second argument is 0, we throw a runtime exception. So this code will just work. The problem with this I have with this code is that its signature says, given two doubles, I return a double. But the actual behavior of this code is, given two doubles, I either return a double or I crash your current thread. Because that's basically what a runtime exception does. It says, crash the current thread. And the only way I know that this is the behavior of the function is because I took the time to write some Javadoc on top of my function saying that this can actually happen. And of course, everybody here always writes Javadoc on top of their functions explaining this behavior. And of course, before you call a function, you first check the Javadoc if it can actually throw a runtime exception. But if you don't do that, I hope the tests are good. Otherwise, you might have some nice, nasty surprises in production. So runtime exceptions do work, but they do have some downsides. It crashes the thread, and it's hard to see that it can even happen. But this does make them good for unrecoverable errors, because if you can't recover from this error in any way anyway, then you might as well just crash the thread. So if your error is unrecoverable, then runtime exceptions are actually quite a good solution. Another thing I see in Java quite a bit is returning null if we don't know what we should do. I actually really hate this approach in Java. As I told before, I hate null pointer exceptions, and the best way to solve those is just not returning null. So the problem here, again, it has the same issues as the runtime exception, that the signature is given to doubles, I return a double. The behavior is basically I might return a double or probably cause a null pointer exception somewhere else. And in this specific example, you might be able to see it because, hey, we have a capital double here, but in most cases, if this would return a function, everything is null in Java. But the biggest problem I have with returning null is that what happens to the function calling this function? Well, this function can return null. So what do? You have to do a null check. Fine. But what do you do when it's null? Well, that function will probably return null itself, which means the function now calling that function also needs to do a null check. And what does it do if it's null? Well, I might as well return null myself. And now the function calling that function needs to do a null check. And before you know it, your entire code base consists all of null checks, just because one function at the bottom starts returning null. And this is why I don't like returning null. There are luckily other options in Java. We have checked exceptions, optionals, and sealed types. So checked exceptions, who here likes checked exceptions? Can you give me a thumbs up? Actually, a few people liking checked exceptions. Usually this is the point where everybody say they hate checked exceptions, which I can understand, but the checked exceptions aren't all bad. Because if you take a look at what a checked exception actually tries to do, first of all, it shows the method can fail in its function signature, because you can clearly see this function either returns a string or it throws an exception. So suddenly I can immediately see this function can go wrong. It also shows in that way that the function has multiple return types. It has a happy flow and an unhappy flow. What it also does, it offers the higher context to recover from it. Basically saying, hey, something went wrong in me. I can't recover from this, but instead of crashing the thread, I want to give the option to all my callers to decide what needs to happen. Like some callers might just crash the thread, but other callers might be able to use a default value instead. So basically, what you're saying is, I'm not making the decision to crash the thread. All my callers can decide for themselves what's best within their context. It also forces people to reason about the errors. You have to do something with the fact that it can go wrong. And they're fully type checked. So in a way, checked exceptions are great for recoverable errors. But for some reason, they are not very popular. And basically, I can think of two different reasons. First of all, the API is absolutely horrendous. The fact that we need to have this whole try-catch block around it, that's just not very easy to work with. And ironically, a lot of checked exceptions are things like file not found exception, which in a lot of context, file not found exception means, yeah, then the process just stops. Basically, in a lot of context, file not found exception is an unrecoverable error. So yeah, of course, people get annoyed if they continuously have to basically say to the compiler, no, I can't recover from this anyway. And so yeah, I can see how checked exceptions can annoy certain programmers. But what they try to do is actually quite decently. It's just the implementation isn't that great, in my opinion. Luckily, since Java 8, we now have the optional type, which basically tries to do the same thing as a checked exception, just with a far better API. And you can decide for yourself which errors are recoverable or not. So Here, our function signature is given two doubles, I might return a double. So it's very fair in this function signature. And the nice thing about optional is that it's great. That means it's great for recoverable errors, because you can recover with either or else get, or even or else throw if you was just like, well, crash if I can't recover from it, just crash. It's composable with map and flat map things. But the big downside is it doesn't have error information. So if a function returns an optional and it's empty, so why is it empty? Is it, for example, because no database record could be found, or that the database connection didn't work? So why is it empty? Luckily, we can also fix that. This bit of the presentation is more about thinking for how functions actually work, and also to kind of show off a bit what the new language functions in Java 21 can do for us. Because if you think about it and take a step back, functions basically either return a success or a failure. So we can also model this in our type system. So if we would make a sealed interface, this is a Java 19 function, that of result that's either a success or a failure, then suddenly we can model the return type of a function. The fact that that the interface is sealed means that the compiler knows these are the only two possible implementations of the result interface. That's why that's needed. We'll cover in a few in slide or two. If we then change our divide function to return a result instead, so if b is 0, we return a result.failure, and otherwise we return a result.success. What we can now do is use Java 21's new pattern matching and pattern match over the result, saying that if it's a success, we can do a certain thing. And if it's a failure, we can do another thing. We can basically create these branches in code. And notice there's no default statement here. That's because it's a sealed type. So the compiler knows these are the only two possible implementations. And if we would ever add a third, this switch statement will no longer compile. So this is fully compile time safe. But this way, we can basically have everything the optional gives us, plus we can have the error information saying exactly what went wrong. And in functional programming, we call this an either. So if you ever see an either in functional programming, this is basically the idea behind it. It's just an optional with added error information, and the optional is basically just a better checked exception. So functional programming isn't all that difficult. So the key takeaways here are: think about your error path. And every time you see an error path, think to yourself, is this a recoverable error or is this an unrecoverable error? And also take into account, is this error unrecoverable for me, or could a higher context recover from this in any way? So the lower your function is in the function hierarchy, the more likely you want to say, oh, this is probably, I want to offer the higher context to recover, because I don't want to make a decision for all possible code flows that are touching me. And runtime exceptions are not your only option as a Java programmer. Especially now we have Java 21, we start be able to have actual eithers and such. So really looking forward to the Java 21 age. And this brings us to the final subject, side effect management. So functional programming, we love pure functions. And a function can be called pure if it has these three properties: idempotent, total, and referentially transparent. So what do these terms mean? Well, a function can be called idempotent if it's repeatable. So basically, if you call it with the same arguments, you will always get back the same result. Even if it's an exception, as long as it's always given the same arguments, you return the same exception. A function being total means that a function should have a valid output for every possible input, which roughly translated basically means you're no longer allowed to throw an exception, because an exception isn't a valid output of a function. If your function throws an exception and you want to make it total, a trick we can use is, for example, make it return an optional instead. because now, no matter the input, you will always get back an optional. The optional might be empty or not, but you will always get back an optional. So using things like an optional, that's a way to make what we call a partial function a total function. Or if we really want to go into functional programming, an optional is a monad. So we can use monads to make partial functions total functions. But we can forget about that terminology. And the last one, this one is slightly more difficult to explain, is referentially transparent. And the best way to explain it is basically if you could replace your function body with a lookup table. So for example, if we have the plus function that takes 2 arguments, if you could take the implementation of the plus function, if we could change it to this lookup table where the first argument is 1, the second argument is 1, so the result must be 2, or the first argument is 1, the second argument is 4, the result must be 5. So if we can replace the function body with a lookup table, then the function is referentially transparent. What this means for the rest of your code is you cannot alter any state outside of the function. And you cannot use mutable states from outside of the function. Because if any of these 2 things are true, then you can no longer replace the function with a lookup table, because the result might be different because it uses state from outside. And if a function has these 3 properties, we can call it pure. And pure functions are really nice because they're extremely reliable, extremely consistent, and very easy to test. By definition, you don't need any mocks to test a pure function. So what are things that prevent a function from being pure? These are things we call side effects. And very popular side effects are any form of I/O, like reading or writing to files, calling a web service, calling a database, the combination of getters and setters, because the setter will mutate a variable outside of function scope. So that's no longer referentially transparent. And if a getter uses that variable, then it uses mutable state from outside this function scope. So that one is also not referentially transparent. Getters by themselves are pure functions, if the variable is immutable. But also things like logging. Like a log statement writes something to standard out, to console, and probably even to file. So it alters state outside of the function scope. To be fair, I usually don't see logging as a side effect. So you don't have to be that dogmatic about logging. But as you can also see, we need side effects. You can't make an application without side effects. But they do cause the problems, because these are the things that make our application unreliable. And these are the things that make our application hard to test. To give an example of that, how would you test this function? So we have a function here that tries to calculate the amount of seconds between now and the date we pass. So first we get now, then we calculate the amount of seconds, and then we return. How would you test this function? Well, the official answer is, yeah, they actually did a lot of thinking by making the new datetime API, and there are actually ways to test this function. But the big problem here is that this line makes the function really difficult to test, because it gets the current date. Another way to look at this problem is that time is actually a hidden input into this function. So instead of, because time is, the time gets added to the function in this line, we cannot, don't have control over it through our inputs. And that is what makes the function hard to test. And we can see that if we make the hidden input an explicit input, suddenly our function becomes incredibly easy to test. The same goes with, for example, if you want to do some I/O over a file. So if you want to see if a file exists or not. In here, the file system is the hidden input of the function. Because if the function would be given a file name and a file system, suddenly the function would be very easy to test, and it will always be consistent. But because we don't want to pass a whole file system into a function, yeah, then the file system remains a hidden input into the function, and therefore it can suddenly go wrong. And the same goes, as you see, with time. as long as it's a hidden input of our function, then things can go wrong, and that's what makes things hard to test. Another example of this is also what I see a lot, is that a lot of code combines logic with side effects. So if we have a function that first looks up a user in a database, then do some arbitrary business logic, and then stores the user in the database again, this function is also quite difficult to test. I mean, we can do it. We can either use mock the database, use an in-memory database, or use a test container. Like, there are ways to test this function, but it's not trivial. You also have to make sure the database state, everything is correct. So this function is quite difficult to test. So how can we improve upon this? Well, it's very easy. We look at what the side effects are, this and this, and separate them from the business logic. So if instead we do this, suddenly our full function is still difficult to test. Like, our application needs side effects. So we will still have functions which will be difficult to test because we need a side effect within our application. But our business logic suddenly is very easy to test because it only cares about the user. It doesn't care where the user comes from, and it doesn't care where the user goes to. It only cares about the user. So by separating business logic and side effects, well, while our application as a whole still is difficult to test, at least our business logic are now pure functions. And these are very easy to test and extremely consistent. And for this, we can use a pattern that I like to call the orchestrator pattern, where we basically have an orchestrator that calls a side effect, for example, get something out of the database, does all the checking required, all the error handling, everything. Only when everything is correct, we pass it to the logic layer. It will give an answer back, and then the orchestrator will handle the result, for example, by storing it in the database again and do all the error handling. This way, all the side effects are the simplest possible thing they could be. The logic is a simple possible thing it could be, and the orchestrator basically only does orchestrating and error handling. So this way, every component is the simplest it could possibly be. And if we do this pattern more and more and more, we will see that we will basically create a pure domain layer, which is extremely reliable and extremely testable. And around it, we'll create an anti-corruption layer that handles all the side effects. And if you would put this into a drawing, you would get something like this, where the domain in the center, corruption layer around it, and around those are our side effects. And this is usually the point where I ask if people recognize what this picture looks like. This is the picture that you described, a hexagonal architecture, or onion indeed architecture. So basically, the whole reason why hexagonal or onion works is basically it's just side effect management. So on one hand, I'm quite happy it has a new name where side effect management becomes more popular again. But basically, we've known side effect management since the 60s or something. This is nothing new. So onion and hexagonal are great architectures, but if you already do side effect management quite well, then you're already pretty close to doing this stuff. So at least now you know why this architecture works. So the key takeaways here is you need side effects. We can't write software without side effects, but at least try to be conscious about them. Every time you see something, try to identify, is this a side effect or not? And if they are, try to make them explicit and maybe separate them from the business logic. And if you do this over and over again, you automatically end up with a hexagonal / onion architecture. So concluding today, composition is a very powerful tool that can help you with problem solving. Be careful with state. There's nothing inherently wrong with mutable states, but try to use immutable states first and only use mutable state for pure performance gains. And if you do that, try to keep it function scoped. Don't trust the happy path. Basically, hope isn't a great strategy, and there are other options than runtime exceptions. Be aware of side effects and at least choose where they take place. And most important, be pragmatic, not dogmatic. You don't need all these things in all applications you're writing, but the more complex your application gets, the more of these things you probably need. And if you already do a lot of these things, well, then you probably might already be a lot more of a functional programmer than you might think. So if you find this subject interesting and want to talk more about it, feel free to add me on Twitter or LinkedIn or whatever. You can also find any recordings and slides on my website. If you are looking for some mentoring and such, again, I'm on codingcoach.io. Feel free to contact me there. I would love to help you. I think knowledge sharing is incredibly important, and I'm very passionate about that subject. And if you want to look back at just the sheets, you can find them on this URL. And with that, I would like to thank you all so much for your attention, and thank you for having me here. And if you have any questions, feel free to ask them, or just add me on LinkedIn or send me the things on Twitter, and I'll be happy to answer any questions of you there as well.
Thank you so much, Tees, for that very insightful session. I'm sure that our participants here really enjoyed and learned a lot this afternoon from what you've shared. And actually, there are a lot of questions posted in the Q&A tab, so I'm just gonna breeze through some of them, and I hope you still have the time and energy to answer these questions. All
Okay.
right. We have one question from Ryan L. What is the future direction of FP? Do you think it will be widely adopted or even replace OOP?
It will definitely not replace OOP, but that's again because I don't. Both paradigms are very strong within their own context. So most software would benefit in using both object-oriented programming and functional programming. So in that sense, I don't think it will ever replace it, but I do see a trend that the combination gets way more popular, that people start being more and more conscious about what functional programming can bring. So yeah, it will never replace OOP, but I do see it becoming a bit more popular. And the future direction is applications will be a combination of the two.
All right. Thank you, sir. And thank you, Ryan L., for that question. Our next question is from Rainiel. What resources or books would you recommend for learning functional programming in depth?
Oh, that's a difficult one. There is, I can post in chats, a friend of mine, Alejandro, who works at the JetBrains, is the Kotlin language architect there. I actually had a lot of good discussions with him, and he wrote a book that basically has the same view of things as me, and he actually is very good in explaining this in book form. So I can, as a resource, I can post his this link to his book there.
Okay. Or you can just post the materials in the resources tab, sir.
Yeah.
All right. Another question here we have from JC. How can developers stay at the forefront of FP advancements?
Best way to do it is to actually go into projects where they do functional programming and to go to conferences. And basically, I don't know, there are certain advancements in functional programming, but I think for a lot of people, it's mostly basically starting out with, if you do a lot of root cause analysis, you end up with the fundamentals of software engineering, which is very close to functional programming. So basically, keep on doing root cause analysis. Why do you do a certain thing? Why do you do that? Why do you do that? If you ask yourself these questions over and over again, you automatically start understanding functional programming a lot more. And a good way to do this is actually teaching. A lot of things I learned are from teaching others, because they keep asking the question, why do you do that? And I never want to give the answer just because. And otherwise, try to program in functional programming languages like Scala. Kotlin with the Arrow library is actually quite popular, and I'm a big fan of that. So shout out to Arrow. Those are the ways that I try to do that.
All right. I hope you got some tips there, JC. Our next question is from Francis Carl. Would you also recommend FP in a dynamically typed language like JavaScript?
This is a bit of what the definition of FP we use here. That's why I hate kind of the definitions OO or FP as such. I try to look at more of a software engineering fundamentals level. So what is actually hardcore functional programming? Like all the concepts I talked about today can be applied in any language. Some allowed it are much more suitable for them in the sense that they support these things a bit more than others. But in JavaScript, you can still be thinking about side effect management. You can still think about errors. You can still think about state management. It's just you might need to do a bit more effort to make objects immutable, for example. But nothing in JavaScript prevents you from doing any of these things. And TypeScript is actually quite a good language for functional programming.
All right. Thank you, sir. We have another question here from Francis. No, from Andrew. We have, when there is a state change in a record type in Java, does the record type keep track of the entire object states or just the states that were changed? So coming from a .stack implementing domain events as immutable states.
Yeah, so a record can't change state. So it has a certain state. If you create a new record that contains part of the old state, you would just, in that sense, I'm trying to understand the question here, you still have, if a person would have a name and an age, you would increase the age. You will create a new person object with the same name as the previous one with a different age. It does mean that both objects will point to the same name. But because strings are immutable, this is a safe thing to do. If objects are immutable, it's safe to have multiple pointers going to the same object. This is also the reason why sometimes immutability can actually be better for performance, since it's safe to have multiple pointers going to the same object. So there's no keeping track of any state. You create a new objects, but they may have pointers to the same things that previous objects have pointers to. I hope I understood the question good there.
All right, thank you, sir. Andrew, I hope that answered your question. Another question here from Ronaldo. Can we truly write enterprise-grade applications using only pure functions and no side effect programming, or are we using the wrong tool or programming language for the job?
Well, we can't make an application without side effects. We can only make an application that handles side effects. And a lot of applications have been written in this paradigm. So the answer is yeah, we can make enterprise applications with mostly pure functions and handling side effects. And again, we need side effect, but we can prevent certain side effects, as mutable state is also side effect. We can prevent those by using immutable objects, and most languages support that. So yeah, definitely we can do this, and even in Java, you can get very far in this. It just requires a bit more discipline here and there.
Correct. Thank you, sir. Thank you, Ronaldo, for that question. Another question, actually, a lot of the remaining questions are citing examples, sir. So I'm just gonna read more of those kinds of questions. So can you cite one of your favorite open source program that uses FP?
Again, the concepts are used in pretty much any software. But yeah, I already mentioned Arrow library. It's a functional programming library, and I really love that library. So Arrow would be a good thing to look at.
Perhaps, are you an ambassador of Arrow?
No, but I gave a talk about Arrow before because at some point I was programming Kotlin, and I had the same problem where the Kotlin's nullability system is like the Java optional, and I had a problem. Yeah, but I want to have to know what went wrong, and the result type wasn't available in Kotlin yet. So I looked at the internet, and then I figured out, oh, this Arrow library can help me with that, and I got really excited about that. And And then I also know the people behind it, like the book that I was about to recommend. That's also one of the people who wrote the Arrow library. They're really clever people, very passionate about what they do, and very good in sharing the knowledge about it. So I really like what they did with Arrow. And it's a lot more easy to get into than, for example, language like Scala. So Scala is a good way to learn a bit about functional programming and such, but Kotlin with Arrow is a lot easier to get into.
All right. Perhaps, Manuel, you can check out Arrow as recommended by Sir. So another question here from Gabrielle. Can you give examples on when to best use functional programming and when it's not recommended?
Okay, that's in a way it's always good, but again, if a lot of functional programming is complexity reducing. So if you have a trivial program that just gets a file and just reads a file and puts the contents on the screen or whatever, yeah, those are trivial bits of software. If you try to add monads and optionals and all those kind of things to that bit of software, yeah, you'll make it more complex. So in the sense that if your application is completely trivial, you probably don't want to use any of these things. But yeah, the more complicated stuff, you kind of have to start using these things. So, and at least the way of thinking behind it, like being conscious about state, being conscious about errors, being conscious about side effects, you always need that in any bit of software you're writing. And now it becomes an option to choose to ignore that.
All right. Thank you again, Gabrielle, for that question. I think we only have time for one last question. So let me just read this last question from Anna Law. Could you cite an example of downside runtime exception?
Downside of runtime exceptions. Well, basically that they crash the current thread and that you can't see them in the function signature. So yeah, again, there's nothing inherently wrong with runtime exceptions. The thing is, but these are two big disadvantages. And if you go more to the functional programming community, they absolutely hate runtime exceptions because of those things. I'm a lot less dogmatic in that sense that for unrecoverable errors, they are actually quite good. But for recoverable errors, they usually are not the best option available.
All right. Thank you again, guys, for sending those questions. Thank you, Tees, for answering all of their questions. So, guys, if you have more questions, I think Tees posted earlier his socials, so you could reach out to him. Feel free to reach out to him personally if you have more questions for him after this session. But once again, thank you so much, Tees, for being with us in this year's SoftCon 2023. And guys, thank you for joining this afternoon's session. And before I let you go, once again, I would like to remind you that we have a leaderboard, so kindly engage and participate in all the functions here in the platform. And for the hybrid ticket holders, our gates open tomorrow at 7:30 a.m. at the SMX Aura convention. And for our virtual ticket holders, our live streaming will start at exactly 8:30 a.m. So stay tuned. Once again, thank you guys, and see you in the last session for today.